So what we will do in this lecture is try to see the way in which a so-called universe or a population is related to all possible samples of a given size that can be drawn from that population. And it is this relationship which is very important, and it gives us the real sense of what the two properties that we are going to discuss eventually later. In fact, most of the statistical theory and inference needs this. One is the property of being unbiased, and other is the property of having minimum variance. So whatever estimator or the function or the formula that we use are supposed to have these two properties, namely unbiasedness and minimum variance, which is also often called efficiency. These are the important properties whose efficiency or unbiasedness is understood only in the sense of all possible samples being related to the population. And that's what we will be doing in this lecture. So to begin with, let us look at a hypothetical population. This population is really very small. It is deliberately kept small because then we will be able to meaningfully understand what it means to relate all possible samples on the one hand and the population on the other. So this is a population of say households, A, B, C, D, E, F are the 6 households. This is our universe. This is the size of the household, that means the number of persons in a given household. And given these data on the population as a whole, if we had a chance of observing all possible elements in the population, which in this case is evidently feasible, there are only 6 households. So if we have the data on population as a whole, what data we have? We have the population of number of persons in each household, and what can we do with this data? So one simplest estimator, that means one simplest formula that we can use to process this data pertaining to a population is to find out what the arithmetic mean is. And if we do that, computing arithmetic mean with equal probability as we have seen, we take the sum of these, which is 30, and there are 6 households. Therefore, simple arithmetic mean would be 30 divided by 6, which will give us the mean household, that is simple arithmetic mean household size equal to 5. Of course, the mean or any central tendency parameter is usually meaningful only when it is reported with the associated variability, or what is called a measure of dispersion. So we should also calculate not only mean, but we should also calculate something that can be called as the dispersion, and we'll be using a more popular measure of dispersions with which usually students are familiar from their introductory courses on descriptive statistics. What we do is, if this is something which is in between, and that's the way in which the term mean used to be used at one point of time, we have an extreme observation like 8, we have a relatively small observation like 3, and the mean lies in between, and that is 5. So we ask the question, if this is something which is a meaningful average description of the household, how much does each household varies from this measure? And one way of doing that is to subtract mean from each of the individual observations. That means 8 minus 5, that is 3, 6 minus 5 is 1, 3 minus 5 is minus 2, 5 minus 5 is 0, and so on. This is minus 1, minus 1. Evidently, arithmetic mean is always a measure which is a balancing point. So if we measure the distance of every individual observation from them, these distances would always add up to 0. But then we have a problem. If the distances add up to 0, then how can we talk about the average distance for each household? That is something which is a problem which can be solved in 2 ways. One is, as you can see, the real problem emerges because there are these observations which are negative signs, these observations which are positive signs. But if you take the sum of all negative and the positive, they cancel each other, annihilate each other, and that's why you get the measure of the dispersion around mean equal to 0. So problem may be due to sign, so I can ignore this sign and add up. If we do that, then that is something which is called the mean absolute deviation. I'm ignoring the sign. When it is negative, I consider it to be as if it is positive and add it up. This is also a good measure. But we'll return to a more popularly used measure. Another way of getting rid of the signs is not ignore the signs, instead take the square of it, because all these are real numbers, and if I take their squares, the square of a real number is always necessarily positive, so the sign can be get rid of, and we will get the sum of squares of the deviations from the mean phi, and the sum of square of this deviation is equal to 16. Why do we square it? In fact, this squaring has a link with our usual notion of distance in geometry. For example, when we want to measure a distance between 2 points, what we do is we join those 2 points, construct a right angle triangle around it, and take the squares of those right angle triangles, add them up, and take the square root. This is precisely what we are implicitly doing when we are measuring a distance like this. So, squaring is a process which is often associated with Euclidean distance of a Pythagorean type. So, this is the sum of squares of distances of each individual observation from the mean value, that is simple arithmetic mean value, and that is 60. Now the question is, this is what is called a variance or a quadrants, because they are sum of squares, and we can divide this by what? We can divide by 6, because there are 6 observations. That won't be right, because even if we have 6 observations, we could not construct these measures with 6 observations. We can construct these only with 5 observations in genuine independent sense, because we have to first fix the mean, without which we cannot define a distance, and therefore, in a way, whatever 5 observations I take and add them up, the remaining observation would be such that the sum total of these will produce 0. So we don't have really 6 free observations. We have got only 5 free observations. This is what is formally recognized as the loss of degree of freedom, when in order to estimate 2 kinds of parameters, for example, simple arithmetic mean and the variance associated with it. At the time of mean, we have got 6 independent observations, but when we fix a mean and impose that mean on the very same observations, then we lose 1 degree of freedom. Therefore, we have 2 choices, either pretending as if we have got 6 observations, I can divide 16 by 6 and I will get this as a measure of variance. But if I am careful enough and I say that the genuine free observations that I get are not 6, but 5. So 16 divided by 5 is 3.2. So this would be the variance with n as a divisor, this would be the variance with n minus 1 as a divisor, and this is important. This is adjusting for what we call degrees of freedom, correction for the degrees of freedom. So we are not dividing n equals 6, but instead we are dividing by n minus 1, because the loss of degree of freedom equal to 1. Why? Because we have fixed the mean from the same data and imposing mean on that data to measure something that can be called as a departures from the mean. Therefore, the free observation that we have genuinely got is not 6 but 5. What does it really mean? That means if I take out of 6, if I take 5 derivations and add them up, their addition will always be in sign opposite but in value equal to the 6th derivation, and therefore it produces 0. So we have what the notion of what is called degrees of freedom. Of course, as you can easily imagine, when n, that means the sample size, is going to, or the total number of observations are going to be very large, then dividing it by, say for example, 98 and 99. For example, when n is equal to 99, and then n minus 1 would be 98, and dividing by these 2 numbers will not produce terribly high difference. In other words, if the size of observations that we have got are very large, then it does not necessarily always matter whether you are dividing it by n or n minus 1. But in case of small samples, it does definitely matter. Therefore, we are going to take n minus 1 as a divisor, but not only because our sample size is small, but there is something more to it, which we will return to this point later. But just observe, if I take n equals 6 to define variance, then the variance of this population would be reported as 16 divided by 6, which is equal to 2.67. Whereas with variance with n minus 1 as the divisor, that means 16 divided by 5, it will be equal to 3.2. So please note this, we have got 2 measures of variance, one with without adjusting for the gross degree of freedom and one with adjusting for degree of freedom. And then eventually we will see why the adjusting for degrees of freedom matters in some sense. Okay, so we have got this information about population, but our problem in sampling is not really knowing the whole population. We computed all this just to understand what are the parameters, what are the things that characterize population. In other words, this is a population whose average household size is 5 persons and the variability associated with them is 3.2. So if I now take root of this will be something which is akin to what we call standard deviation. So in fact 3.2 under root will be the standard deviation. Strictly speaking, 3.2 under root divided by n will be the standard deviation. So we have the variability associated with the arithmetic mean in form of either variance or standard deviation. In most of the cases, we don't bother to really convert it to the standard deviation because the variance is a more convenient quantity which is additive and so on and so forth. So, in fact, in many cases, we don't really bother about dividing by n as well. Later we will see when we look at the least square or many operating with the several kinds of estimators or the formula, if both the numerator and denominator have got the same divisor, why bother to divide them? So, we can also look at what is traditionally called simply sum of squares or sum of square corrected for mean. That is also a very important statistic whose sampling distribution we are going to see a little later. So we have got this population characterized by arithmetic mean equal to 5 and the variance with n minus 1 degrees of freedom equal to 3.2. Now let us try to relate what are the samples that are possible. As we had indicated earlier, there are, if we draw from this population sample size of 2, how many total such samples are possible? If we look at that, then we can see that there are several samples that are possible. If you look at this, for example, instead of, I can take AB, AC, AD, AE, AF. This is a listing of 15 samples that we had defined last time. So if there are 6, C2 will be equal to 15, so there are all 15 possible samples. So here is the listing of all 15 possible samples. And for each of the sample, we plug in those values. That means take value of A and value of B as it is there in the population, plug it there in place of A and B. The sum would be there for 8 plus 6, that is 14. When it is A plus C, it is 8 plus 3, that is 11, and so on. So for each of these, we calculate total, just as we calculate arithmetic mean. For each of the population, we can also define the arithmetic mean for each of these samples, and these are the listing of all arithmetic mean. For example, if the sample is AB, the arithmetic mean is 7, AC 5.5, AD 6.5, and so on till EF, where it is mean is 4. So these are all 15 possible sample means. So if there are total 15 possible sample, for each of the sample we calculate sample mean, and for that sample mean what we do is we calculate. Now I'm going to use small y because I have used capital Y for the population, and that's usually a convention in sampling theory textbook. The samples means are usually reported with a lowercase letter, whereas this is the capital or the uppercase letter. So if I take all possible 15 samples, that means there are several y bars. How many y bars we will have? We will have 15 y bars. So for the first sample to 15 sample, if I add up all sample means, there are 15 possible samples. If I add up all sample means, then what do we get? Then we get the sum of all sample mean equal to 75. So if we, for example, it's here, we get it equal to 75. And when 75 is the sum total of all sample mean, so if we calculate what can be called as the mean, that is simple arithmetic mean of all possible sample means. What do we get? The simple arithmetic mean of all possible sample means, that means all 15 possible sample means, would be 75 divided by 15, which is equal to 5. And now you can look at this number 5. Is it something which the number which has appeared earlier? That number is in fact exactly equal to population mean. When we had all 6 possible households of the universe, what was the mean of the population? The mean of the population is 5. And what do we get here? Mean of all possible samples drawn from the same population of a given size. If I take the mean of all possible sample means, it is equal to population mean. That means y bar, capital Y bar, is same thing as what can be called as mean of all sample means. And that is same. And it is this property which is a very critical property. This is one of the reasons why arithmetic mean happens to be most frequently used, most extensively used kind of a formula, or what is technically called estimator, because it has got this property. If I now restate this in terms of what is called a population and sample in probabilistic language, what I am saying is, when it is a mean of all sample means, the typical used term for this is what is called expected value of y. The expected value of y, that is for the population, that means y bar, is always equal to, if we take the expected value means what? Mean of all possible means. Expected value is a term which is typically used to denote a situation where, like arithmetic mean, we did not necessarily confine ourselves to equal probability. Even if it's unequal probability, whatever are those unequal but real probabilities, we attach them, what you get is called expected value. So the probability weighted mean is something which is being referred to more generally, hence the name expected value of all arithmetic mean is equal to population arithmetic mean. So a more general definition for this purpose therefore is, whenever the formula that you are using, what is the formula that we are using here? It is the arithmetic mean which we are using here. If we use arithmetic mean weighted, that is differentially probability weighted or equal weighted, one of the properties is that if we take the arithmetic mean and if we take all possible sample arithmetic means and if we take the expected value of all arithmetic means across samples, it is always equal to population mean. This is the property that if the expected value of all sample parameters, now in this case the parameter is arithmetic mean, if the expected value of all sample parameters is, when I am saying all sample parameters, it means really all possible sample parameters of a given size is equal to the population parameter, then the formula that we are using, that means the estimator that we are using, is said to have the property called unbiasedness. So if the simple arithmetic mean of all possible sample mean is equal to simple arithmetic mean of our population of values, then simple arithmetic mean would be considered as unbiased estimator of the population mean or population parameter. Now the reason we use the term parameter is, in this case we have calculated mean, therefore here we mean by parameter arithmetic mean, in fact a simple arithmetic mean, that means equally weighted, that means equal probability sample mean, but it need not be so. Later we will see when we extend these ideas to other formulas such as, for example, estimating slope parameters on the basis of sample data. There the parameter would really mean slope, not necessarily arithmetic mean. But what is important at this stage that you should understand is that arithmetic mean, as we have already discussed in last lecture, is a linear function of sample values or the population value. So as an estimator, as a formula, it's linear in nature, and it has got a property that if we use that formula repeatedly across all samples of given size, the expected value of all sample results is necessarily equal to the population mean or population parameter. Hence, it is supposed to have the property called unbiasedness. So we have got in form of arithmetic mean, weighted or simple arithmetic mean, that is equal probability arithmetic mean, it is linear in nature, A, and B, it is unbiased. So you can take it to be P and U. It is L and not P. It is linear in nature and unbiased in its properties, in its characteristic. So arithmetic mean is a linear, unbiased estimator of the population parameter. It is this idea that we are, this notion of a property of an estimator, the formula with which we calculate or estimate the parameter. It is the formula which is supposed to be unbiased. And what do you mean by unbiased? The definition is here. If we take all possible samples of a given size, and if we take the expected value of all those possible sample parameters, it must be equal to population parameter. That's the notion of unbiasedness, and it is true for the simple or weighted arithmetic mean. And hence, simple or weighted arithmetic mean is an unbiased and linear estimator. It is this notion that is going to repeat itself in a variety of ways, particularly where later we will see that the regression coefficient that we estimate from the sample data is also supposed to be linear in character and unbiasedness. So now let us see, if this is the case that we apply in case of arithmetic mean, can we extend the same notion to geometric mean? Can we extend the same notion to harmonic mean? So one can take this as a theoretical exercise. If arithmetic mean is unbiased, is geometric mean necessarily unbiased? Suppose for a moment, forget about unbiasedness. Is it linear in nature? So as we know, as I had shown it in the last lecture, it is linear only under transform condition, not the original data, because original data is product of all observations, and obviously it is not linear in nature. So linearity is one property, unbiasedness is another property. Now similarly, as we are talking of arithmetic mean or harmonic mean, etc., let us also talk about the variability, because the mean or any central tendency estimate is meaningful, is useful when it is read in conjunction with what can be called as the measure of dispersion. What is our measure of dispersion? Our measure of dispersion is take the mean value, subtract it from the other values, that is the distance from the mean, square it, and sum all such squares of deviations from the mean, and then divide by n, or alternatively divide it by n minus 1. Now in this case, in a way, we have much less computational burden here, because here what is the n? In each sample, n is equal to 2. So what is going to be n minus 1? N minus 2, n minus 1 would be equal to 1. So we don't have to really divide, we can only simply take the sum of squares itself as the measure of variance, if we are using the formula of variance which has got n minus 1 as the divisor. Of course, if it is n, then you will be required to divide it by 2. Now let us see what kind of a measure of variance do we get. For example, if we take this sample variance with divisor n minus 1, because as you can check it from this, sample mean is 7, and if we calculate for both observations the distance from them, square them, sum them, it turns out to be 2. Now like this we continue with all possible 15 samples, and if we do that, so we have got 15 samples, therefore we have got 15 sample variance estimate, and sum total of all those 15 sample variance estimate is equal to 48. Please note what we are doing here, just as we did in case of arithmetic means. We calculated all arithmetic means, 15 arithmetic means, then we took the arithmetic mean of all arithmetic means, that means 75 divided by 15, which gave us the value of population mean equal 5. Does the same thing happen with this? Now you can again check, we have got the 15 variances, add all 15 variances. So this is the sum total of all 15 variances. I divide these 15 variances, sum of 15 variances by 15. The answer that I get is 3.2. And now you can see that the answer that I have got is 3.2. If I had divided this by 2, it will not be same as the population variance. So if I get an estimator with n minus 1 as the divisor, then I get unbiasedness as a property with the variance. That means for retaining the unbiasedness of the estimator, that is a formula, adjusting for degrees of freedom for the mean already calculated is relevant. So having n-1 as a divisor imparts a property to the variance measure of that of unbiasedness. If I stick to n as the divisor, it will not naturally hold. Only argument that one can make is when samples are very large, the difference would not be very significant. But nonetheless, when I am going to take variance with n-1 as a divisor, I am quite sure that even for small samples, it's going to turn out to be unbiased in nature. So between variance, that is sum of squares from the mean divided by n, or sum of squares from the mean divided by n-1, that is adjusting for the degree of freedom that is lost because we have calculated mean from the same data, and it has got therefore one imposed condition that sum of deviations must add up to 0. We adjust for those degrees of freedom and make it as n-1. But taking that n-1 as a divisor gives me a measure of variance which has got unbiasedness as a property. So if I take again the expected value of all 15 variances and compare it with the population, then it turns out to be the same when we have used for population n-1 as the divisor. Again, remember, for all 6 households, when we calculated the measure of variance, it was 3.2. Again, here it also turns out to be 3.2. So the unbiasedness is a property which is applicable both to arithmetic mean as well as to the variance, but in case of variance, one has to carefully choose the appropriate degrees of freedom. And adjusting for appropriate degrees of freedom is an important idea, and unless one has dealt with the sampling theory in the sense of repeated sampling theory, one will not come to know what significance it has, particularly when it comes to dealing with the distributions such as t-distribution or chi-square distribution or f distribution. Adjusting for these degrees of freedom is a very critical, important ingredient of the entire statistical argument. So we have got now a method by which we can now see that the way in which all possible sample parameters are in some sense related to the population parameter. In what sense? For example, if I take all possible sample means, take their mean, I find that it is equal to population mean. Similarly, with appropriately adjusted degrees of freedom in case of variances, if I take the sample variances for all possible sample and take the expected value of all those variances, it turns out to be again population variance. So we have got these two formulas, one pertaining to computing mean, that is arithmetic mean, and other pertaining to computation of variance. In either case, they turn out to be unbiased, and they are also linear in nature, because all that we did in this case is again sum total of the variances being added up within sample, and while relating it to the population variance, we took the sum of all variances and add them up. And this is something which is always possible when the outcomes are independent. That means they don't have a common subset of element of covariability, etc. So this is important result. We can do the same exercise by asking a question: what if from the same population of 6, if I took 3 households at a time? Again, calculate all possible samples of size 3. How many of them would be there? Again, you can have this, but I would like you to do this as an exercise which is easy to do. You can do very quickly in the Excel sheet, for example. These are the listing of all possible sample observations. These are all possible samples, 20 all possible samples, because evidently it is now not 62, but instead it is 63, where the answer would be 20. So there are 20 possible samples of size 3 from this population of size 6. So if I do the same exercise for each of them, I calculate mean, I calculate variance, and so on. And this is something which again we get and again verify that the results that we have got are in fact same and similar to the result that we got for sample size 2. Now what is the purpose of doing this? The purpose of doing this is to see the way in which drawing sample and knowing about one sample, our job is to know about the remaining samples, and in that sense our job is to know about the entire population. So if I know one of these samples, will I be in some sense including what is there in the population as a mean. So if I got a sample mean, will I be closer to population mean? Now this requires a notion of sample means being spread around the population mean. And that is precisely what we mean by distribution. It is a sampling distribution. Means what? If I take the population parameter and if I try to relate the sample parameters with the same formula, in what sense are these sample results related to the outcome that I will get for the population as a whole? That's the whole notion. And the idea in that is that if we have a population parameter, and that population parameter must be in some sense related to sample parameter. And what do you mean by that? I would like to have, for example, I know the population mean. In this case, we know, say, y bar, capital Y bar equal to 5. And if I have got most of the sample values which are in fact around this, then I would say that using sample of whatever given fixed size would still in some sense retain me closer to what I am interested in. I am interested in this population parameter, what is the mean household size for the population as a whole. But I can't observe the whole population. Instead, I can observe only a small fraction of it. But that fraction and the outcome given by that fraction by a formula says, for example, arithmetic mean or the variance, is going to be close enough to this value of y bar equal to 5 for the population as a whole. Then I think doing sampling makes sense. It must be in some sense close. That means I don't expect every sample will give me exactly same value. In fact, as you can easily see, if it's sample size 2, we have 15 different kinds of means. If we have got sample size 3, we have got 20 different kinds of means. Not all of them are necessarily equal to 5. But the question is, are they in some sense around 5? How many of them are around 5? This is something which is the notion of distribution. That means, for example, if I plot them in terms of a histogram, I intervalize this data and put them in terms of frequency. Do I get, if I get a histogram something like this, and if I find that most of them are going to occur in this, then I will say most of them are going to give a result which will include population mean. Or alternatively put, I can also think of most of the sample means being in fact in and around the population mean. In fact, it is one such important property in case of the linear estimator such as arithmetic mean is that the shape of frequency distribution that you will get for all possible sample results, that is summation xi, forget about dividing it by n because we know the n has a fixed value and it only scales it down, nothing more, or scales it up if it's negative population. But we have most of the values. That means what can be said is, suppose I know x bar, which is a population mean, in our case it is y bar, y capital, and there are several x bars, that means small x bar, x1 bar, x2 bar, and so on. So suppose if I have got k such samples, now these samples would be in sense of a histogram, in terms of a spread, in terms of the frequency of their occurrence, will always be distributed around this. And as we have seen, in case of arithmetic mean, if I take the expected value of all of them, then in fact it will be equal to it. The very fact that it will be equal to it shows that they would be in some sense closely clustered around the population parameter. And it's not only that. What we know is that as sample size increases, and if I take a repeated sample, very large size, then I can talk about the kind of shape that I will expect will always occur, irrespective of what kind of a population from which we have drawn a sample. The shape will turn out something like this, which probably you might have learned, which is called often the normal distribution kind of a curve. It is symmetric, U-shaped, at least in this portion, and then it is spread over asymptotically to both the ends. This kind of a distribution, which is called normal distribution. We are going to resort to use of normal distribution in a variety of ways. For example, in test statistics, we are going to use normal distribution, and then we are going to use chi-square distribution, which also, as degrees of freedom increases, again converges to the similar kind of a size, similar kind of a shape. So normal distribution is a very essential idea, a very important idea, and it doesn't matter what kind of a population. Take any population and define a sample size of a reasonable magnitude, and you keep on taking repeated samples and define arithmetic mean for each sample, then you will always find that approximately the spread of the frequency distribution of all sample means will always be around population mean in this kind of a shape. That is something which made statistical theory capable of variety of inferences. This is a property that can be mathematically shown. In fact, one simpler way of looking at it is to in fact look at something like binomial distribution and you generalize it for a very large sample, then in fact you get a limiting value of binomial distribution to a normal distribution, and that's how De Morey actually discovered it to have binomial. Though in now new textbooks we do it the reverse exercise, we approximate binomial probability of very large size on the basis of normal. But historically speaking, it is a limiting curve that De Morey was able to discover by exploiting it binomially. So, normal distribution, that means normal distribution means having different frequencies and being spread, and arithmetic mean is always approximately normally distributed in the frequencies. That means if you take a histogram of this type and join those points, you will get a curve like this. And this is something that one can see. So I have not plotted it in form of a curve, but instead in terms of what can be called as a clustering. And you can see that this clustering is visible in the data that we have plotted here. Now you can see this, I don't know whether this fits in completely. Doesn't matter, n is equal to. If you look at, we have taken the intervalized data. If the sample size is 2, you can see that most of them are spread around population mean. Here is the interval where population mean is contained. And now you can see as I increase the sample size, for example, n equal 3, then n equal 4. Now you can see that with n equal 2, the spread is much larger. With n equal to 3, spread shrinks somewhat. With n equal to 4, there is a significant shrinkage to the spread around population mean, and it is more densely distributed. Same for the 5 and so on. So this is the basic idea, that as you increase the sample size, not only that sample means are distributed around population mean in this kind of a shape, but in fact the spread that you have got also starts shrinking as the sample size increases. Naturally, with increasing sample size, you being in the vicinity of the population parameter of your interest is going to improve. That's the reason why having more number of elements in the sample or having a higher sample size is something which is often beneficial, because we are likely to be relatively lot more sure of being at the target that we want to know, about, such as, for example, population parameter size, population mean. So this is what is the basic idea, the sampling distribution of a formula. Please note what we have done. We have chosen a formula. We have actually used two formulas. One is the formula of computing arithmetic mean. Second is the calculating the variance based on that arithmetic mean. We applied this formula to population. We applied this formula to all possible samples drawn from that population of a given size. And if we look at the way in which these different sample outcomes in terms of arithmetic mean and the variances that we are getting, the way in which they are spread around the population parameters. This is the basic idea. So what we are looking at? We are looking at the distribution of a formula. What do you mean by distribution of formula? Distribution of the values that we get generated by the formula in repeated sampling procedure, and that's why it is called sampling distribution. It is a distribution of the results that you get in all possible sample notion, and if you look at the spread of that, and if you look at the shape of frequency distribution that you get, if that is something which is known a priori or could be mathematically calculated independent of sample size, at least in terms of direction, at least in terms of tendency, then probably we would be able to talk about the kind of results that would occur in repeated samples without necessarily knowing what the all possible samples are. That is something which is the major statistical result, that we know the sampling distribution of a statistic called summation xi, or sampling distribution of summation xi square, which we used in case of variance. It is this distribution which is known mathematically, which is tractable mathematically, derived mathematically, independent of the values that are going to occur. That means the values can occur in whatever range, the best possible largest range being minus infinity to plus infinity. Still, the shape that you get of that frequency distribution of sampling outcomes remain invariant to that. It is approximately the same every time. It is this property which is useful in making statistical inference, in making statistical guess about what is it that we want to know by observing a small fraction, and from that we would be able to imagine, guess, conjecture about the remaining samples and therefore the remaining the total population that we have not seen. So this is the crux of the statistical reasoning. The important idea is sampling distribution of the results of the formula, that is the estimator, when applied in repeated sampling to sense what kind of a shape, what kind of a frequency distribution curve do they generate. If that distribution curve is tractable mathematically, independent of whatever values that actually occur in the population, then the problem of sampling can be very meaningfully and conveniently solved. And that is something which is one of the major discovery that was made by de Moivre in form of discovering the normal distribution. So when we talk of distribution, it is a distribution of what? It is a distribution of not only sample parameters, but it is in fact a distribution of, that means behavior of the formula which is used to process sample observations. It is the property, it is the frequency distribution associated with the formula and not values per se. Whatever be the values, the shape in fact remains more or less the same. That means it is independent of values. It is the frequency distribution of the outcome that you get in repeat sampling generated by a formula, hence it's a distribution of that estimator. It is a sampling distribution of the estimator that we are interested in, and that can be in fact mathematically tracked, and that is the essential point that one must understand, on the basis of which several possible further statistical arguments, such as the arguments that we make in terms of statistical inference, are feasible, are sensible, are valid, precisely because we are talking of the behavior of a particular estimator in repeated sampling procedure.